Hello and welcome to this review of more applied titration calculations. Obviously, being more applied, you'll need to have had a look at the more fundamental titration calculation techniques that you've done some notes and independent study on, and we'll be using the DMEMA technique, or data moles equation moles answer, that's been covered before. So often the substance of unknown concentration in a titration will be the solution of a solid. So we need to be able to use the titration to obtain information about this solid. I've outlined a few little attempts at pictures of the equipment you'd need. So going through the procedure, the first thing to do is to obtain the mass of your solid sample by using a top pan balance and a weighing boat. So you fully dissolve your solid sample into a small amount of water in a beaker, transferring this with rinsings into a volumetric flask before making up to the mark. You then use a glass pipette and filler to transfer an accurately measured sample of this solution, and this is called an aliquot, this sample, to the conical flask under the burette. And finally you titrate the aliquot against a standard solution in the burette to obtain the moles of solute, the original solid, in the aliquot. So the last thing to do is to work out the moles of solid you originally had in your sample that you weighed. So to do this, you take the moles of solid that you've now calculated in your aliquot, which I've labelled for you on the diagram, and you multiply this by the volume of the volumetric flask over the volume of the aliquot titrated. So in other words, you scale it back up. Okay, so I think it's time to try an example question that requires you to do this. So here's one possible type of exam question where you have to identify an unknown base using a titration and starting with a solid. So first thing to do is to lay out your data moles equation moles answer type calculation layout. So I start by selecting the data for which I can actually work out the moles of something. So in this case it's going to be the number of moles of HCl, my standard solution that was used. It's my standard solution because they've told me the concentration of it, 0.200 moles per decimeter to the minus 3. So that gives me 4.26 times 10 to the minus 3 using N equals V times C. So that means I can state that in my moles section. If I look at the equation, it tells me that the number of moles of HCl and the number of moles of XOH are the same. So this tells me that the number of moles of XOH in my aliquot is also 4.26 times 10 to the minus 3. So we can work out from that the number of moles of XOH in our unknown hydroxide sample, 2.39 grams, we can use the same scaling up as we did before to obtain the number of moles of XOH as 4.26 times 10 to the minus 2. The fact that it was added to 250 centimeters cubed of water in a volumetric flask, or at least made up to 250 centimeters cubed in a volumetric flask. So 1/10 of that was used. So because 1/10 of the original XOH was actually titrated, the moles are scaled up by 10. So you can rearrange moles equals mass over molar mass to work out the molar mass of XOH as 56.1 grams per mole to the minus 1. So if we take the hydroxide ion, Mr of OH, is 17.0 grams per mole to the minus 1. So by difference you can work out what the relative atomic mass of X is, and by checking against the periodic table, 39.1 grams per mole to the minus 1 gives you potassium. And potassium, being a group 1 metal, will form a 1-to-1 ratio with hydroxide ions, and therefore the hydroxide, the identity of it is KOH. Now you can also use titrations to obtain the water of crystallization in a hydrated salt. Obviously the hydrated salt has to be a base, in order for this to work, because it's based on the acid-base reaction, isn't it? So therefore, the titration to obtain X in XH2O, they might ask you a question about that as well. So we've got a typical exam question. This particular type of exam question is a bit harder than the one we looked at a couple of minutes ago, because there's two things to do. First, you have to do the DMEMA calculation to deal with the titration, and then you have to follow that up by moles of water of crystallization calculation. So I'll take you through each of those two steps separately. So as normal, we start by working out the moles of the substance we have enough data for. In this case, it's the HCl. So fast forwarding through the process slightly, hopefully you can follow it fairly easily. Using the data, you could get 2 times 10 to the minus 3 moles of HCl reacted. So therefore, the number of moles of sodium carbonate to the number of moles of HCl from the balanced equation is 1 to 2, so therefore that gives us 1 times 10 to the minus 3 moles of sodium carbonate in our aliquot. And therefore that gives us 1.0 times 10 to the minus 2 in the sample. And the scaling factor is times 10, because 25 centimeters cubed goes exactly 10 times into 250. So therefore we know we have 1.0 times 10 to the minus 2 moles of anhydrous sodium carbonate in our sample of hydrated sodium carbonate. So when you're dealing with water of crystallization, what you've got to think about is the fact that a hydrated salt contains a certain number of moles of anhydrous salt to a certain number of moles of water. So essentially what we're trying to work out is the mole ratio of anhydrous salt to water. So we're now looking for the mass of anhydrous Na2CO3 in the sample, and we achieve this by multiplying the moles times the molar mass of the Na2CO3. So multiplying those together, that gives us 1.06 grams of Na2CO3 anhydrous in 2.86 grams of our original hydrated sodium carbonate. So the mass of the water present in the sample of hydrated sodium carbonate is 1.80 grams. So if we convert this into moles using mass over mR, it gives us 0.100 moles of water present. So if we insert these numbers into our little diagram, we can see that we've got a 1 to 10 ratio. So that gives us a value of 10 for X, and therefore the formula of the sodium carbonate hydrated version is Na2CO3.10H2O. Okay, so hopefully this has been a fairly useful extension clip to take you through to some more difficult and applied titration style calculations you might come across at A level. It's now worth going and having a look at some exam papers, some past papers, and see if you can seek some of these out, or perhaps look at your textbook and see if you can find some particularly tricky looking examples and see if you can apply some of these ideas across. But in the meantime, until next time, thanks for listening and see you soon.